Okay, so going to start by reviewing what we did last week. So talk about adversaries and round-based models. We'll go over that again, and then I'll talk about shellability and what that is, and then give you a basic theorem about how shellable complexes act under round operators. And then probably not this time, but next time we meet, I'll talk about applications of this theorem to all these different models. So far we've been talking about weight-free computations where all but one process can fail. And that's kind of a standard in this business, but people also like to talk about T-resilient, where up to T where you write your algorithm so that up to T can fail. Now, that's in the real world, failures are usually not correlated. Sorry, failures are usually correlated. You can have two processes that live on the same server or live on the same network, and they don't fail independently, but they fail in dependent ways. And so you can imagine a system where these two might fail together, but not this one, or this one might fail, but not these two. And so what we want to do is to generalize the notion of failure models to be able to capture each of these possibilities. So we're going to capture this with something called an adversary. So an adversary controls when failures happen. The adversary controls scheduling up to a point, so that if we're in a synchronous model, the adversary has to be synchronous. If it's asynchronous, the adversary has more freedom. So the adversary has constraints, but subject to those constraints, it can choose whatever will cause the most mischief. So the easiest way to characterize a failure model is by talking about faulty sets. That is, these are the sets of processes that can fail. So here you can say, well, these two might fail, or that one might fail. That's a simple characterization of an adversary. And the going to make a technical assumption, which is that faulty sets are closed under containment, meaning that if both of these can fail, then it's possible that only one of them can fail. So you can't write algorithms that require processes to fail for your algorithm to work. And you can imagine that if I told you that all but one, the faulty sets were every set of n-1 processes, then you can solve consensus simply by waiting until all but one had failed. And we don't think that's a very interesting model of computation. But we need this technical assumption in order to make the proofs work. So we never require a process to fail, although we have to be able to tolerate it. So we're going to, one way to capture this is something, we can capture the set of failures as a simplicial complex, where we have a vertex for each process. And I'm going to put a simplex around every faulty set. So this says that these two might fail. And then our assumption says that actually it's also possible that the individuals might fail. But because there's no vertex linking red and blue, red and purple, that means that we don't expect both of these two to fail simultaneously. So the absence of an edge means that we don't need that there's no simultaneous failure. And so this, for example, is the failure complex for the irregular failure pattern I showed you before, where these two processes live on the same physical server and are likely to crash together. The weight-free failure complex is just the n-1 skeleton of the simplex. It just says that any set of n out of n+1 processes can fail. T-resilient is the T skeleton. In this case, T is 1. Failure. Yeah.
The T is 1 and the T-1 skeleton.
Here we say that T can fail where T is 1, and so this is basically the 0 skeleton.
The skeleton of points is called 0.
Oh yeah. So this is the 0 skeleton in this case. One, so it's one, yeah, there should be T minus 1 skeleton, you're right. The
n or n minus 1, n plus 1 process.
So here, this is the n minus 1 skeleton, which is every set of n. This is the usual.
N minus 1 is 1. What is n here?
Here n is 3. No, n is 2. N is 2.
N is the dimension.
Yeah, and n is the dimension. But t is the number. So this is what's confusing is we're counting in different ways here. Now, keeping track of failure sets is kind of awkward, and that's more information than we really need. So we can condense all the interesting aspects of adversaries into two dual ideas, cores and survivor sets. So a core is just a minimal set of processes that cannot all fail. So, for example, that means that it is safe for your algorithm to wait for at least one member of any particular core to show up. So I can write an algorithm that says, sit around and wait until you hear from some member of a particular core. And I don't have to worry about that my algorithm will never terminate, because some member of the core will always appear. So what does that look like in terms of our failure complex? So here's our failure complex for our irregular pattern. So a core is any minimal simplex that's not in the failure complex. So in this case, these two, red and purple together, are a core, because they can't both fail. Green and purple are a core, because they can't both fail. These are the minimal simplexes that have this property. All three of them can't fail too, but that's not a core, because that's too big. Smaller simplexes are not cores because they can fail. So this is the set of minimal. This doesn't constitute a simplicial complex because it's not closed under containment.
So but minimal by inclusion, not minimal in size.
It's no, it's minimal in dimension. Minimal by inclusion, yeah.
So
if there were a bigger core. You could have, say, another core that had 3 processes. So it's minimal by inclusion, not minimal by size. That's correct. And so our irregular failure complex, the cores look like that. Weight-free failure complex, the only core is the entire set. So the only set of processes that we know aren't going to all fail is everything. So typically, if you're writing a weight-free algorithm, you can't wait for some member of a core to show up because you yourself are you might be the process you're waiting for. T-resilient failure complex, any set of T+1 processes is a core. Because they can't, only T of them can fail by, so any T simplex in this case is a core. So for a lot of models, all the models that we're going to look at later on, the minimum core size completely determines the adversary's power to solve any colorless task. So as long as your task is a colorless task, and most of the tasks we've looked at so far are colorless tasks, the only thing that matters is the minimum core size. And they're given a particular minimum core size, there can be lots and lots of different adversaries that have that core size, and they're all equivalent. So that if you can solve an algorithm against one adversary, you can solve that algorithm against any of these adversaries. That doesn't mean the same algorithm will work in every case, because your algorithm might start out by waiting for some member of a core to show up, and if the cores are different sets, then the same algorithm won't work, but you could transform any algorithm written for one model into an algorithm that works for the other. Okay, there's a dual notion that sometimes comes in useful, although we won't use it quite as much, which is the idea of a survivor set. So a survivor set is a minimal set of processes that might all survive. So remember, a core is they can't all fail, and this one is they might all survive. And again, we're interested in minimal size. So it says that if you have a kind of a barrier and you want to wait for a large number of processes to show up, it's always safe to wait until you see a survivor set. So as soon as you see a survivor set, you better stop waiting, because you're not guaranteed that anyone else will show up. But it's always safe to wait for some survivor set to show up. It's not safe to wait for a particular survivor set to show up because that might not be the set that actually survives. But you know which sets are survivor sets, and it's okay to wait for one of those. And these are dual. They're basically hitting sets for one another. So if you give me the set of cores, I can produce a set of survivor sets and vice versa. So they don't contain any more information than cores. They're just somewhat more convenient in some cases. So here's our irregular failure complex again. So a survivor set is any simplex whose complement is a simplex in the failure complex. So in this case, these two, the red and the green process, are a survivor set because blue might fail, and these two might survive. Blue by itself is also a survivor set because red and green might fail and blue might survive. So those are the survivor sets. The wait-free failure complex, any individual process is a survivor set because you're guaranteed that somebody's going to survive, but you don't know which one. So here too, the set of survivor sets is kind of degenerate. So any vertex is a survivor set. In T-resilient, any set of n minus t plus 1 processes is a survivor set. So any n minus t simplex is a survivor set in this case.
So for a survivor set, if the complement fails, then necessarily the survivor set
might succeed, but it also has to be minimal. So there might be some execution where a large set survives, but if there's another execution where a subset of that survives, then we pick the subset and not the larger one, because it's not safe to wait for the larger one.
Does the duality hold also when you don't, when the adversary is not closed under containment?
When the adversary is
one of these things that break down when you remove this.
I'm not entirely sure, but I think it might break down. There are all kinds of places where it's really hard to write algorithms for things you want to do in the not contained model, and it's really easy to write the ridiculous algorithms that can solve impossible problems if it's not closed under containment. So we don't like that model. Okay, so that's what an adversary is. So when we talked about proving connectivity of complexes, what we did, we gave you several examples of critical state proofs. We did a critical state proof for path connectedness. We did a critical state proof for n connectedness. And the basic idea is we argue by contradiction. So we assume that the protocol complex is not k-connected, or that the reachable part of the protocol complex is not k-connected. We show that you can always go to a critical state, which has the property that no matter what happens after the critical state, it becomes k-connected. And then we say, well, what could be happening at this critical state? How could these processes be interacting with one another? And then we use model-specific arguments to derive a contradiction and show that it is impossible to transition from being not k-connected to k-connected at this critical state. And because we know we're eventually going to be k-connected, it must be the case that we were k-connected all along. And this is the essence of the FLP style proofs. And so this is a very general and powerful way of proving things, but it has some limitations. In particular, it seems to work best for asynchronous models. It's hard to make critical state arguments work in synchronous models where everyone takes steps at the same time. I mean, you can sort of do it, but it's not very nice. And you remember what we did when we talked about all of the possible interactions in the critical states. We talked about conflicting reads, conflicting writes. There was a big case analysis where we look at all the possible ways operations can interact with each other. And if you start looking at more exotic models, like what happens if I have reads, writes, test and set, and compare and swap? Each new operation I introduce means I've got a whole other list of interactions to worry about. And so the proofs become very long and tedious fairly quickly. So instead, what we're going to look at here is a alternative way of proving things, which is a kind of invariance proof, where we say, well, if something's k-connected before, we're going to break the computation down into small steps and show that if we're k-connected before we take the step, then we're k-connected afterwards. And that the k-connectivity is a kind of invariant. So rather than saying it isn't, oh, there's a contradiction, here's a big case analysis, we'll show that if your complex is k-connected before you take the step, then after you take the step, this property is preserved. So it's an invariant-like argument.
So when in the 3 slides back, you were talking about if it was connected before, it wouldn't be disconnected after, rather than...
Yes, yeah, so here we argue, we assume it's...
If it's not connected and later connected, you actually want to reason that if it's connected and later disconnected, you get a contradiction, right?
Well,
Because otherwise you're invariant.
No, there's no contradiction because we're sort of pushing all the things forward. We say this is connected, we're going to analyze what happens in this step, and then say, behold, it's connected afterwards too. So there's no contradiction in this style of argument.
Right. But what you meant 3 slides back then was that if it's connected before, it will be connected after. Not if it's...
Yeah, but the way to argue that, yeah, it is sort of a way of saying that if it's connected here, then we can sort of pull back and get connected backwards. So it's really a backwards argument rather than a forward argument.
Okay, well, pick it offline.
Yeah. But so in order for this to work, we need these steps to be small and manageable. And so what it is we're going to look at basically round by round computations, where each process, the processes execute one round, and then when they're done with that, they move on, they do another round, and then so on all the way until they're done. And this round by round sounds like a synchronous notion, but also works in asynchronous models. This is similar to communication closed layers and all of this other stuff. So we're going to break the computation down into a series of rounds. In the synchronous world, this is simple. It's the same round at the same time. In the asynchronous world, I might be doing one round, and then a week and a half later, another thread could be doing that same round. So they don't have to happen at the same time. And we'll treat connectivity as an invariant. If it's true before, then it's true after. And we're not going to have any critical states or contradictions here, so it's a much more kind of uniform method. And the nice thing about it is that if we want to mix and match different operations, we can say, well, we can split it so you can do your reads and writes on even numbered rounds and your tests and sets on odd numbered rounds. And then we just prove individually that each of these rounds preserves the invariant. And we don't need to worry about all the polynomial number of interactions between the operations. So this is sort of the model that we have. So this is the state of the world, the protocol complex at some point. We apply the round operator, we get a new complex, we apply the round operator again, and then keep going till we get to after R rounds, we end up with this one. And what I'm going to show, and this is very deliberately expressed at a very high level, that if the initial state is k-connected and satisfies certain niceness properties, and the round, the carrier map that defines a round has a nice local property, meaning we're going to talk about how it acts on an individual simplex. If it has this property, then the complex is still k-connected and still has nice structural properties to keep everything going. And then, given that kind of invariance, we can push this forward until we run out of rounds. So typically what happens is if the round operator does not force any processes to crash, which is typical of asynchronous models, then we can keep this going forever. In synchronous models, the round operator may force some processes to crash, and sooner or later we run out of processes to kill. And so that means that we can only run for a certain number of rounds. We can only preserve connectivity for a finite number of rounds. Okay, so the nice property that is going to help us do things is a notion called shellability. So here, the basic idea, shellable implies that you're, peeling a banana or a nut or something, but it's easier to think of it as putting a complex together rather than taking it apart. So the idea is I want to build up this complex by taking n simplexes and gluing them together along n minus 1 faces. Now, all the complexes we're going to look at here are what are called pure, meaning that the facets, their largest faces, have the same dimension, although this definition works even if they're not the same dimension. So here, for example, I'm taking two triangles and gluing them together along an edge, so that's shellable. Here, I'm doing the same thing, but now I'm gluing it together along two edges, and that's shellable. Here, I'm taking this edge and gluing it in along three edges. And that's basically, with triangles, all you can do, 1, 2, or 3 edges.
So when you say that something is shellable, you mean these pair of triangles are shellable, or when you, what is the object?
Oh, the object is a simplicial complex.
The complex,
Yeah.
single complex.
Yeah. So the simplicial complex is shellable if I can build it by starting out with one triangle and then gluing it together, where by triangle you mean simplex of appropriate dimension. And so in order to show that something is shellable, that means there exists a way of building it this way. It doesn't have to be unique. In fact, it typically isn't unique.
Can be different dimensions?
They can be different dimensions, but we won't need that here. Everything here will all be the same dimension.
Are only simplexes of one dimension? The maximum simplexes are only of one dimension?
They don't have to be. So the definition works if they're not. But all of the complexes that we're going to talk about here, the top dimension, the largest complexes all have the same dimension.
And also, you fix a number, say 3, and then each maximal simplex should be glued to 3 other simplexes?
No, it can be, it can be any. So with triangles, it can be either one. I can glue it with 1, 2, or 3.
And in the same complex, there could be 1 and 2
And 3 edges. And it could be the case that I could be gluing this to a lot of different edges at once. So I could take, say 3 triangles and I'll glue them together like this. Well, like in a 3-way thing. So it's not a manifold. So a shellable complex is not a manifold because you can have many complexes glued together along faces.
The property is that just that you are gluing 1 minus the dimension of the
Yeah. So you take you have n complexes, you take n minus 1 faces, and you glue along n minus 1 faces. And that's what makes something shellable. Now, so here is, I'm going to give you a couple of equivalent definitions. So this one is kind of intuitively appealing, but a little bit awkward to work with. Then I'm going to give you another definition that's easier to work with, but not quite as elegant. So we'll say it's shellable. So a facet is a face of maximal dimension. So we'll call it a facet just to save words. In a diamond, the facet is a flat face. So we can take the facets and we can arrange them in a linear order, like this, phi 0 through phi sub k. So we kind of line them up in order. And for every k, this should be less than, not less than equal. So I'm going to pick a k, and then I'm going to take the union of everything that comes before it in the order. So this is just a more formal way of restating the gluing picture that I showed you before. And now I'm going to take the intersection of phi k with all of its predecessors. And I've highlighted this here. So phi k intersects phi 0 at one point, phi 1 at an edge, phi k minus 1 at a point. But what's important is that it intersects phi sub k at an n minus 1 face. And so this intersection here is the union of faces of phi sub k of dimension 1 lower than phi sub k. So in this case, it says that the intersection here, in this case it's an edge, but it could be 2 edges, or it could be all 3 edges. But it cannot be an edge and a point, for example.
Equals a union, not the union, right?
Equals a union, some union. So this is, So we can write it in symbols. And we say that this is phi k intersection everything that is ordered before it in the Schelling order. If that is a union of dim phi sub k minus 1 faces of phi k. So again, this is just pictures and symbols to say the same thing, that you're gluing these triangles along their edges, or the tetrahedrons along their triangular faces, that kind of thing. So I'm going to make a kind of a topological aside that we're not actually going to use, but it's going to motivate some of the things that we're going to do, which is that if you know that a complex is shellable, you know a lot about its topology, just from the fact that it has to be built this way. So here, for example, we'll say that any simplex that gets glued on by all of its edges is called a spanning simplex, because it kind of spans this hole. And if we're asking what's the kind of topology of these things, what does it look like? Well, I can take this thing and I can contract it to a point, because it's really just a disk, topologically speaking. I can take it and sort of squeeze it into a point without ripping anything. And then if I do that, then this thing contracts into a sphere because all of its edges are being pulled into a point. And so in this particular case, this is the same as a sphere. And so the shellable complex is homotopic to a wedge. Just means you take spheres and you glue them all together at one point, like a bunch of balloons. And so every spanning simplex defines a sphere. So that tells you what the holes are like in a shellable complex. You just look at you pick any Schelling order, you find the Schelling or the spanning complex simplexes, and that's the number of spheres that you get. So in particular, this tells us a lot about the connectivity. So if C is shellable and each facet has a dimension greater than or equal to k, for some k, then it's k minus 1 connected, because it's just a bunch of k-dimensional spheres. I'm not going to prove this. It's you can look it up in any book, but that says that shellability is yet another way to prove connectivity. So if I want to show that something is k-connected, one thing I can do is I can show you that it's shellable by giving you a Schelling order, and then say, look, each of the facets has a dimension k or greater, and therefore it's k minus 1 connected. And that's basically what we're going to do in a number of models of computation. So let's look at some examples of shellable complexes to kind of build up your intuition. So this is a sphere. Of course, it's not really a sphere, but topologically it's the same as a sphere. It's an octahedron. And I claim the spheres are shellable. How do we know this? Well, we'll start out with a single triangle, and I'm going to show you how to build it up by gluing it together along edges. So first thing I'm going to do is I'm going to attach, these are the triangles that I glue on by attaching along one edge. Now I'm going to attach triangles along two edges. And then I'm going to complete it by putting in the spanning simplex, which completes the sphere. So that's evidence that a sphere is shellable. Before we actually try to prove things are shellable, I'm going to give you a different formulation of shellability, which is completely equivalent to the one I gave you before, but it's easier to work with. It's easier to prove things this way. So again, I have this complex K. I have these facets lined up in a Schelling order. And the requirement is that for every phi sub j, every triangle in the Schelling order except for the first one, I'm going to pick an I less than j. So I'm going to pick this one here. And for every pair j and every preceding simplex I can find a phi sub k that has to be less than j. It could be earlier or later than I, we don't care. It could even be equal to I, we don't care. But it has the following properties. So the intersection of phi I and phi sub j has to be contained in the intersection of phi k and phi sub j. So in other words, the phi I and phi j might intersect in only a single vertex here, but I can find something here that intersects it whose intersection with phi j contains that intersection. So in some sense, if all I care about are intersections, then I care about this one because it's big, and I don't care about that one because it's small. In some sense, the intersection is absorbed into the larger one. And then I want the dimension of the intersection to be basically in a n-1 face. So these two intersect in a maximal face. And so that means, it sort of means I could ignore this one because the intersection is already contained in that. So what I need to do is I need to show that given any phi sub j and any phi sub I that comes before it, I can find a phi sub j that basically absorbs this intersection and that intersects in a face.
Only the absorbing is definition, the maximum is
I need both of these conditions.
what's the other condition for?
I want that the intersection of I and j is contained in the intersection of j and k. So that this vertex here is contained, this intersection here is contained in this intersection here. Now, it could have been that if this intersected over here, then this phi k wouldn't do. I'd have to find another simplex whose intersection absorbs the smaller intersection.
So you want to find k that satisfies
Yeah.
the same k.
Yeah. No, for every pair I and j, I want to show there's some k. If I change I here, then I might have to change a k as well. And so this is what I'm going to do if I want to prove that a specific sequence is a Schelling order. I'm going to prove this instead of trying to prove the direct statement, which is more intuitively appealing but more awkward to work with. This is fairly straightforward to work with. Okay, so since we're going to be building a lot of orders on complexes, I'm going to define something called face ordering, which we'll use a bunch. So given a simplex sigma, I want to put a total order on its faces, which will be useful for constructing Schelling orders. So here we have an n simplex, and I have a face of that n simplex. So what I'm going to do is I'm going to order all the faces as follows. I'm going to represent each face as a bitmap. So here I'm going to represent sigma, the big simplex, as all zeros. And I'm going to represent this one as all zeros for the 3 vertexes that are present and a 1 for the vertex that's not there. And so I'm going to use 0 to mean that vertex is present in the face. And so every face of the simplex can be given by this bitmap. And the reason 0 means present instead of absent is just that it's easier to work with for the purposes that we will use it for later. Sometimes you could do it either way, but not always. Okay, so for example, here, the least simplex in this ordering is the entire simplex, because we're going to compare these lexicographically. So,
Partial order.
beg pardon?
This is a partial order.
No, it's totally ordered because we're going to do a lexicograph. We're going to compare the first 2 digits, then the next 2 digits. So it's just a linear extension of the, we could do a partial order and then say any linear extension, but I want to make this specific just to keep the proofs more concrete. So here, the entire thing is less than any of its faces. And here we have 2 faces, so this is less than that because these 2 digits are the same, but the second digit, this is less than that. So by lexicographic ordering, this comes first. So the actual order is kind of arbitrary, but it will be easier later on if we have a specific order to work with. Okay, so let's do a kind of a practice theorem, because the techniques we're going to use here will come in helpful when we start talking about more complicated things. So what I'm going to say is, so given an n simplex, I want to argue that the k-skeleton of that is Schellable. So remember, the k-skeleton is all of the faces of dimension k or less. And so what I'm going to do is I'm going to show you that the face order I just defined is a Schelling order. That in fact, if I line up all the faces in the face ordering, then that's a Schelling order. So I'm going to do what I did before and say, okay, so I'm going to pick a facet phi j, and then pick any facet that precedes it in the Schelling order. And I'm going to write down the bitmap representation. This is just something I made up. And so the first digits in this example are the same. So we skip them. And then sooner or later we come to we come to a vertex indexed with L, where phi sub j has 0 and phi sub I has 1. We know that this exists because phi sub I is less than phi sub j by assumption, and that's what it means. So what it says is that there is a vertex that is in phi sub j, because we use 0 to mean present, and but not in phi sub I. So if I take phi sub j and throw out phi sub I, then I have S sub L, which is, this is slot number L.
Reverse the order of 0 and 1.
This is, J is, oh no, I didn't. I reversed the I and J. This should be J on top, and that should be L.
For the whole complex, we have given one particular digit to, given a particular bit to all the vertices, and that is fixed.
Yeah, yeah.
So if we change that order, then this ordering will change.
Yeah. So it will still be shellable because the same exercise will work. The assignment of values here is arbitrary, but once you make that arbitrary assignment, then we can build the Schelling order. And if you were to change the order, then you'd have a different Schelling order. But this is right. This should be J and this should be I, because we want I less than J. But there is a vertex that is in phi j, but not in phi sub I. So what else do we know? Well, because these dimensions are the same, if we put something into J, then we have to take it out. There has to be something in I that's not in J, because they have the same dimension. And so if there's something in J that's not in I, there has to be something in I that's not in J. And so let's assume that happens at index M, where M is greater than L.
So greater is less significant bit.
Yeah. So we must have this situation where we have a vertex that's in I but not in J, and an earlier vertex that's in J but not in I. So what I'm going to do, so we'll remember this. I'm going to build phi sub k by taking phi sub I and putting in S of L and taking out S of M. So that'll give us this signature here, where the red means that I take phi sub I and I change these two digits.
But you start from phi sub I.
Phi sub, sorry, this should be phi sub j. This is confusing because I made a mistake and have the, but this.
But you start from the bigger one.
Yeah.
You make one step toward the smaller one.
Yeah. And so, voila. Okay. Yeah. So we take this, we take the bigger one, and then we give it this missing vertex. We compensate by taking another vertex that's missing down here and throwing it out. And so we need to check, okay, first off, that phi sub k is less than phi sub j, but that's easy because we're doing this lexicographically. And so here, for example, 0 is the same, but as soon as we get here, we have a 0 here where there was a 1 there. So phi sub k is earlier in our construction. We have to check that the difference between the two is 1. That was one of the conditions. And so here, that's also easy to see because we've if we take phi sub I and phi sub j and we throw away phi sub k, well, the difference consists of this vertex that we added, and the vertex that we took away doesn't matter. And then we need to check that the intersection of these two is absorbed in the intersection of phi sub k. But that's also easy because the intersection of these two doesn't have, the way we've constructed it is everything is the same except for these two bits where we've added something and removed something.
So phi sub k might be phi sub I.
Yeah, but that's fine. We don't care. All we need to show is that there's some simplex.
So you look at the difference and you fix the differences, but for the rest it looks like phi sub j.
Yeah. And this, we're going to be doing this same construction over and over again. I mean, this is basically the way that, if you can do this construction, then it's shellable. And there'll be variations on this. Sometimes the order will be more complicated.
So this is a way to walk around the faces.
In some sense, yeah, because it just says that when you glue things together, you can say, what I care about is when I add something, how does it intersect everything else? And so what I'm saying is I don't care about small intersections because they're absorbed in big intersections. So all I need to worry about are big intersections. And that's the intuition, is that when you're adding when you add a new face, it might intersect the existing faces in all kinds of confusing dimensions, but you don't care because if you look at the ensemble of everything that went before you, it intersects nicely on maximal edges, and small intersections don't matter. So this must be a proof because there's a QED at the end.
That's proved by QED.
Yeah.
The only question was the theorem.
Actually, the theorem is that the skeleton is shellable. Yeah. So the other thing, what you're really checking here is that phi sub k is a facet of the k skeleton. But the number of ones is still a k because we took one away and we added one. And we started out with something that had k.
So always the k skeleton is shellable?
Beg your pardon?
Always?
The skeleton is shellable? Yeah.
Always.
Yeah.
It's still the entire simplex.
Yeah. But only of a single simplex. More complicated things might not. I don't know what happens with other things, but this was a simple example. So next thing, let's prove that pseudospheres are shellable, which is what I really want to show. Later on, we'll prove that certain unions of pseudospheres are shellable when we start talking about actual computations. Show you what. Okay, so I'll do this and then we can take a break. Okay, so remember we talked about pseudospheres before. Pseudospheres, we have a collection of process IDs, and we have one set per process. And each vertex is a pair consisting of a process ID and an element from a V sub I. Often these sets are the same set, but sometimes they're not. And a simplex is a collection of vertices with the property that the process IDs are distinct, and everybody gets an element from their own set. And but the thing is that these can be assigned independently of each other, and that's why it's called a pseudosphere. Because, for example, if each V is 0 and 1, then what you get is topologically a sphere, and otherwise what you get is sort of the union of the spheres. And what I want to convince you is that pseudospheres are also shellable, and this is what makes most of what we're doing work. So let's say we have a total order on all of the elements here. So we take the union of all the V sub I and we take a ground order on all of them. It can be anything, arbitrary, anything, any order you want. Now I'm going to argue that we can use that to induce a Schelling order. So here is the Schelling order on facets. So I'm given a facet, which is n processes, each one assigned a value from a V sub I. I'm going to write that not as a bitmap, but just as kind of a vector of the values. And so given any two of them, I'm going to compare them lexicographically using the ground ordering as, so I'm going to compare these two, the first elements and say, well, those are the same. Notice that they're indexed by which process has them. So this has all the same information, it's just written in a more suggestive a way. And then when I look at the second one, I say, oh, they're different. So if u sub I down here is less than v sub I, then I'm going to say phi1 is less than phi0. So we're just going to do lexicographic order on each process's value. And that's going to be our order on facets. Okay, so I'm going to prove this is shellable using the same strategy that we did before. I'm going to say, okay, so suppose I have a phi sub j and an earlier phi sub I in this order. So I'm going to write them down in this kind of vector notation, or string notation, probably a better description, and say, aha, I know that somewhere along the line I'm going to find a matching pair where phi i's entry is less than phi j's entry, because by assumption, phi I comes before j in the shelling order. So we'll remember that. And then I'm going to build a phi sub k by taking phi sub j, same trick we did before. We take the later one, and I simply replace this element with the smaller element, and get this simplex here. And so I claim that this is enough to establish a shellability. So we just check the conditions. So first off, phi k is less than phi j, because when we do the same comparison between phi k, well, the first two elements are the same. The second one, well, this is less than that. And we don't care what happens after that. It's maximal because this phi j and phi k have exactly the same values except for one. So when I throw out everything, take phi j and throw out everything that's also in phi k, I'm left with this one vertex where they're different. And then the intersection is the same because the intersection doesn't contain this. And so the intersection of phi k and phi j contains the intersection with phi j and phi I. And so that's enough to establish shellability of any pseudosphere.
So here, in fact, the intersections are equal in this case.
No, not necessarily, because these are all u's afterwards, but these are all v's.
Oh, okay, sorry.
It was a trap.
Yeah.
So it could be the same, but that's okay. Okay, so what I'm going to do next is show that if your complex is shellable and your round operator has the property that it sends every individual simplex into a shellable subcomplex, then the composition is highly connected. So this is basically going to be our inductive argument for carrying things forward. And so I think we'll take a break and then resume